This chapter starts our study of circuits, and our first circuit element is the capacitor. Capacitors are incredibly useful, and as we go through the chapter, I'll try to talk about some of the uses and why we see capacitors in almost all of our electronics devices. But first, let's talk about what a capacitor is, what it's done, and how we can calculate the capacitance of a device. A capacitor basically consists of two conductors that are electrically isolated from one another. Here I'm showing two conductive plates, and we're going to hook them up and move some charges from one plate to the other. This symbol I drew here is a DC power supply, like a battery, and it supplies some potential difference. The battery is doing the work moving the charge from one plate to the other. The first electron gets moved across the circuit, and it leaves an empty spot behind that becomes like a positive charge. One plate now becomes slightly positive, the other plate slightly negative, and really it took almost no work to move that electron over because there were no charges on that plate repelling the electron, so the battery wasn't fighting anything. It didn't have to do much work moving that first electron. The second electron, the battery has to do a tiny bit of work. It pulls it off of this plate and it's attracted to the positive charge that's there, so it takes a little bit of work. And it pushes it onto the right plate, and there's already an electron there repelling it, so it takes a tiny bit of work to move that second electron over. The third electron takes a little bit more work because it's fighting two electrons that already exist on that plate. The fourth electron, a little bit more. You get the idea. As it moves more and more charges, it becomes harder and harder to move the charges because you're fighting the charges you've already moved. Eventually, it gets to the point where this battery can't do enough work to move any more charges over, and so it basically stops at that point. And if we were to plot that, if we had a battery or a power supply where we could adjust the potential difference, and we started with a very small potential difference, it would just be able to move a few electrons over. And then if we cranked up the potential difference on our power supply or battery, it would be able to move a few more electrons, and eventually it would stop because it couldn't do enough work to move any more. Maybe it could move this much charge. And then we crank it up to a higher voltage, and it moves even more charges from one plate to the other. What we end up with is a curve that looks something like this. The charge that gets transferred from one plate to the other is proportional to the potential difference that our battery is supplying, or our DC power supply is supplying. The charge is proportional to delta V. We want to put an equal sign here, so we need a proportionality constant. We call that the capacitance of this setup. We have, in this case, two parallel conductive plates, and so the capacitance would depend on some of the physical characteristics of this capacitor. And the capacitance, as you can see from our graph, is the slope of this charge versus potential graph. What would the capacitance depend on? The capacitance only depends on the capacitor, the physical characteristics of the capacitor. Things like the shape. How are those conductive plates configured? Are they two parallel plates next to each other? Or maybe they're spheres. Maybe it's a spherical conductor inside of a spherical shell. That would also work. Maybe they're cylinders. Maybe there's a center rod with a cylindrical shell over the outside. Concentric cylinders that are conductive pieces would also make a capacitor. So it depends on the shape. What else does it depend on? The size, the spacing, and, which we'll learn shortly, the material between the plates. But we'll come back to that. Now we'll find the capacitance of a parallel plate capacitor. I'm going to show you the techniques, and you can then use them to find the capacitance of a spherical capacitor or a cylindrical capacitor. It's the same techniques. And the nice thing about this is it's a beautiful transition from last chapter. We're going to take what we learned with Gauss's law and what we learned about integrating the electric field to find delta V, and we're going to use those techniques to find the capacitance of our parallel plate capacitor. These are my two conductive plates that make up my capacitor. Now let's think about what happens if I just had one plate here. The other one was off infinitely far away. If I just had one plate here, and it had excess positive charge on it, half of the excess charge would end up on one side, and half would end up on the other face of this conductive plate. The same would be true of my negative plate that was infinitely far away. It would have half of its negative charge on one face, and half would be on the other face. But when I bring these two plates into the same region of space where they can affect one another, the positives and the negatives attract each other. Some of these negatives are going to move around to the other face because they're attracted to the positive charges over here. Some of these positives are going to move around because they're attracted to the negative plate on the other side. If these plates become larger and larger and larger, more and more charges move around to the inside faces. And if these plates become infinitely large, all of the charge ends up on the inside plate if these both have the same amount but opposite sign charge. If one of them has plus sigma on its face, the other one will have minus sigma. All the charge will move to the innermost surfaces. So let me redraw this. On the leftmost surface of my positive plate, I have a surface charge density of 0. And on the rightmost surface of my negative plate, I have a surface charge density of 0. And I'll call the inner surfaces plus sigma naught and minus sigma naught. They are equal in magnitude, but opposite in sign. Now, sketch your electric field everywhere. Hopefully you have an electric field out here in this region of space of 0. Inside of our conductor, it's 0. And out here on the right of both plates, the electric field is 0 also. Where is our electric field? Only between the plates. And we have a nice uniform constant electric field between the plates, and it's 0 everywhere else. What is the electric field between the plates? We can use Gauss's law to figure this out. I'm going to draw one end of my Gaussian inside of the conductor. There's my Gaussian surface. Remember, you want to put your surfaces either parallel or perpendicular to an electric field where the electric field is 0. And then, of course, one surface needs to be where you want to know what the electric field is, and that's why I have 1 in the middle of my capacitor. Gauss's law, E dot dA, the integral over all three sides of this cylinder, this Gaussian surface I drew, has to equal Q inside of my Gaussian surface over epsilon naught. So let's see how that plays out. This integral just becomes the integral over the left side of my Gaussian surface. Because my Gaussian surface has three sides, I can break it up into these three integrals. The left side, I know the electric field is 0 over this whole face. The electric field is 0 there, so this is just going to give me 0. The curved surface, the side of my cylinder, has a flux of 0 because the electric field lines are parallel to the surface, right? None of them penetrate the surface like this, so the flux is 0. And the right end is just going to be the electric field times the area of the right end. That's this round circular area right here. That becomes E times the area of the end is Q inside over epsilon naught. And what's the charge inside of the Gaussian surface? So let's back up here just a minute. And we're looking at this region of this plate that's intersected by the cylinder. And how much charge is on that part of the plate right there? Well, it's the area multiplied by the charge density, sigma. And the electric field is my charge density, surface charge density, divided by epsilon naught. Now, for a capacitor, we usually are given the area of the plate of the capacitor. It's not infinitely large, but we can approximate it as being infinitely large because the plates are very close together. So for almost all of the capacitor, the area is very large compared to the spacing between the plates. Only in a very small region close to the edge do you have edge effects that change the electric field and make it look like this is not an infinitely large conductive plate. So for our purposes, it's a pretty good approximation to just treat these plates like they're infinitely large. But we're going to be given the area and the amount of charge, and we're going to use that to find sigma. The total charge over the total area is the charge density sigma. So we used Gauss's law to find the electric field between the plates, but we're not there yet. We don't have anything that looks like it might fit our capacitance equation. Which equation am I talking about? This one right here, Q equals C delta V. So the potential difference and the charge transferred from one plate to the other are proportional. And the proportionality constant is this thing we call capacitance. Some capacitors, if you hook up a 9-volt battery, will only store a certain amount of charge. Whereas other capacitors, you hook them up to the same 9-volt battery, and you could get a lot more charge stored on those plates. Or maybe I should say transferred from one plate to the other. We sort of say we're storing charge, but how much charge is there in this capacitor after I've moved some electrons from one side to the other? It's neutral still, right? All I did was move an electron from one plate to the other. I haven't really added any charge to this configuration or taken anything away. I've just separated the charges. I've given them some potential energy. And we were storing some energy in the electric field between the plates. but we sort of loosely say we're storing charge on the capacitors. But really, we're storing energy in the electric field. This is where electric potential comes in. Because there was a delta V in my equation with capacitance and charge, it makes me think maybe I should find the potential difference between the plates of my capacitor, and I have the electric field between the plates from Gauss's law, so I can integrate E dot ds and get delta V. Now, I don't care about signs here. I just want to know the change in potential as I move from one plate to the other. I can look at my plates and I know that the left plate, the positive plate, has to be at higher electric potential than the right side, the negative plate, because the electric field points from the positive plate to the negative plate. I know that from looking at the situation. So all I really care about here is the absolute value of the change in potential. The electric field is constant everywhere between the plates. So the electric field falls out of the integral. The integral of ds is just the distance between the plates. So this is going to be the electric field times the distance. And what distance am I talking about? The distance between the plates. I'm going to plug in my electric field. It's Q over A epsilon naught. I've got my distance between the plates, and this is equal to the change in potential. Now I'm going to rearrange these things. I have a delta V and I have a Q. And remember, my equation up above was Q is equal to C delta V. That was the equation I got for the capacitance. I want to make this equation on the left look like this one on the right. So I'm going to rearrange it a little bit. I'm going to move my Q to the other side. And that's going to be epsilon naught A over D times delta V. Now, this equation looks a lot like this equation. I've got my Q on the left, I've got my delta V on the right, and that means that this stuff here must be my capacitance. Now this is the capacitance for a parallel plate capacitor with nothing between the plates, just vacuum between the plates. If we have a material between the plates, some kind of an electrical insulating material, then the capacitance changes, and I'll show you how to deal with that later. Right now, just think about the thought process we went through. We found the electric field between the plates using Gauss's law because we had some nice symmetry to our problem. We integrated that between the plates to get the potential difference between the plates. And then we rearranged the formula until we got Q equals something times delta V. And we said that something must be our capacitance because we know our capacitor formula says Q equals C delta V. The capacitance should depend on the physical properties of our capacitor. In this case, it depends on the size of the plates, the area of the plates, and how close those plates are to each other, the distance between the plates. You should then find the capacitance, see if you can determine the capacitance using these same techniques for a spherical capacitor. That would be a spherical conductor inside of another spherical conductive shell, or a cylindrical capacitor, a cylindrical conductor inside of a cylindrical conductive shell. So see if you can do that.